Okay guys, welcome back. Now we are going to look at some process improvements to the heat pumping process. So here you have a diagram of something called a open intermediate pressure vessel. And this can be somewhat hard to understand firstly, but I'll try to explain it as simply and intuitive as possible. So the problem here is that if you squeeze something all at once, it gets hot and takes a lot of effort. So that makes the heat pump work harder and waste energy. So instead of squeezing once really hard, we squeeze twice, but gently. So the thing with the intermediate pressure vessel, or the thing that we'll try to solve, said in a very simple way, is that we try to carry a large box up a very high step, but instead of carrying it all at once, we divide the step into two steps. Then it gets easier to carry. So that's what we're trying to do with the refrigerant here. So you can think of this like a rest stop in the middle here, where the refrigerant is gas, some is liquid, and they can separate and kind of calm down here in the middle before everything cools and we go further on. So this helps connect the two sides here, which is let's call this part here the low pressure side. And then the other part here, the top part, for the high pressure side. So we have kind of two loops here. It goes around here, and then this other loop starts here. So they don't have to carry the same amount anymore. They can do what each loop is kind of best at. So it works better when things are cold outside or hot outside, depending on what you're trying to do, cool or heat. So that's the main idea with the intermediate pressure vessel. So the super short summary is that we squeeze in two steps, or we compress in two steps. We take a break in the middle. We stay cooler. We waste less energy, and we work smarter, not harder. So if we look at each step of the way here, we start at state 1. So the refrigerant starts here, is being compressed in the low pressure compressor here. And then we move on so the first compressor only handles part of the total pressure rise. So at state 3, the refrigerant enters the intermediate pressure vessel here, and inside the vessel, liquid and vapor can separate, and the pressure is fixed at the intermediate level. So this is where the system is stabilized at the intermediate pressure. And then from state, so that's state 3, and from state 3 and until state 4 again, the refrigerant enters the high pressure compressor. So the pressure is now raised from medium. Let's call this part here medium, and this part here low, and this part here high pressure. I'll show you this in a diagram in a second. So again, the total pressure rise is split across across the two compressors there. So we have a compressor at the high pressure area here and at the low pressure area here. So from state 4 and to state 5, the refrigerant passes through the condenser here. So the process happens at constant high pressure and the heat is released to the surrounding, as you can see here. So this is the heating part of the cycle. Then after condensation, expansion process is being split into two steps as well, from state 5 to state 6, throttled through from high pressure to medium pressure, and from state 7 to 8 from 7 to 8 here, from medium to low pressure again here. And then from 8 and to 1 again, returning to its initial state, the refrigerant passes through the evaporator where heat is absorbed. So Q in, heat absorbed from the cold source. We can show this in a diagram as well. So in the diagram here, you see all the states. So we have pressure here on the vertical and enthalpy on the horizontal here. So from state to 2, 1 to 2, compressed at low pressure, first compressor, then into state 3 at the intermediate pressure vessel, and from state 3 to state 4 again, high pressure compressor, high pressure, that's looks like a heat pump. Let's write high pressure compressor, and then we have constant pressure through the condenser here. So we have a condenser here, and from state 5 and until state 6, throttled, and then from 7 to 8 again, throttled further from pressure medium to pressure low. So expansion is now carried out in 2 stages instead of 1. So expansion valve and expansion valve here as well. So you can think of this as let's use pressure level high here, pressure high, and then we have a medium, pressure medium here, and the pressure low here. So the key takeaway here is that the open intermediate pressure vessel kind of reshapes the cycle in a way that is much more favorable when the temperature lift is very high. So the diagram here is kind of the visual foundation for understanding why such systems can achieve higher COP than the basic vapor compression cycle, because we're doing things in two steps. The last thing that I want to talk about is that in an absorption heat pump, the compressor used in the vapor compression process is replaced by what we call a absorption loop, and instead of compressing the refrigerant directly, the working fluid is absorbed into a liquid. So the pressure of this liquid is then increased using a pump rather than a compressor. So that's also possible to do and design a heat pump that way. So after that, heat is supplied to the system in order to separate the working fluid from the liquid again. So the key idea here is that the process requires much less mechanical work, but in return requires a significant amount of heat input. So that's just to have said it, that those exist as well. Okay, I think that marks the final point of the heat pump section. I hope this has been interesting to you guys, and I hope that you will ace your exams once you know all the tricks or the dirty tricks that the teachers will throw at you. Okay, thank you guys for this one. I'll see you in the next one.